Okay.
Start. So welcome everyone to Module 2, first session, the overview session. And today we are very excited to be joined by Tyler and Rasul from the PSE group in the EF, which will present the rate-limiting nullifier ZK-DAP. I shared some materials in the kit that contain some concepts that are related to the ZK-DAP. So without further ado, I'll pass the mic to Rasul and Tyler, and we get started.
That sounds good. Thank you. This is Tyler, and so I'm going to go over the rough, idea of how RLN works and some of the design decisions that we've made. And then Russell can dive deeper into the circuits, and we can answer any questions that anyone has. All right. So the point of rate-limiting nullifier is to basically punish denial of service attacks or spam attacks in anonymous systems. So we're going to be going over just a high level of how it works, the building blocks of what make up how RLN works, and then I'll quickly gloss over some of the challenges that we've had. All right, so the kind of core principle behind RLN is proving that you are part of a group without revealing who you are, but also sharing a piece of a secret that on its own is useless, but when combined with other shares from the same user, they can be used to reconstruct who that person was or who that user is. So the share that's generated is unique to the user, the epoch, so that's like just a generic time period, or signal. It could be like a voting, it could be an election, it could be a time period, it could be on a specific post, or any generic like time or uniqueness signal, and then also the message ID. So whatever specific message that the person is sending. So if they send the same message over and over, that could be blocked at like a networking level or protocol level, because the share and the internal nullifier and everything will be the same. If the user, the epoch, and the message ID are the same, it's essentially the same message. So the internal nullifier is a signal that's an output of the circuit that is pretty much useless on its own. It doesn't really do anything on its own. But when more than one internal nullifier match during an epoch, then that is a signal that that you can take the shares from both of those messages and combine them and reconstruct someone else's secret. So, so this is essentially a high level of how semaphore works. It's essentially you prove that you know some secret that hashes to one of the leaves of a Merkle tree. So what comes out of this part of the circuit is basically just the Merkle root and a verification that you know some secret that hashes to one of the leaves. All right, and then the internal nullifier, so this is that unique value that basically shows you that a user has reused or has shared too much during an epoch, that allows you to recombine the shares to reconstruct someone else's secret. So The way this is constructed is using the epoch and the secret, essentially. And the RLN app identifier is basically just a value that allows there to not be collisions between different applications. So you could have, you know, let's say if you use just like Unix timestamps or something for an epoch, then if multiple apps use that, there won't be collisions. You know, if a user uses the same identity on multiple applications, there won't be collisions there. All right, so the way so I saw in the reading that you had Shamir secret sharing as like recommended reading before this presentation, but I can go over that pretty quickly also. So that is kind of one of the key pieces to how RLN works. It's essentially y equals mx plus b. So like, you know, we learned this in grade school, and the secret is the value as it crosses the y-axis. And I can just go over, I'll actually go through the visuals for this. Yeah, so if your secret is 516 or, you know, some other arbitrary number, then we create a point out in space that is derived from the app identifier and the epoch, and then the message and the for our latest version of RLN, it's the message plus a message limit identifier, which we'll get into, determine what the share is along this path. So if you can gather more than one share, then you can reconstruct the line and determine what the secret is as it crosses the y-intercept. So we used to, if you wanted to be able to share more than 2 messages per an epoch, we used to make the degree polynomial for the Shamir secret sharing curve higher degree, which becomes a lot more complex, and it's just unnecessarily complicated. So one of our team members, Lev, came up with an idea to use message limits. So essentially we have a user commits to a message limit when they initially register, and then every message that they send during an epoch, they, in the proof, use a message ID to basically prove that, you know, they're broadcasting a unique message with a unique ID that is within the message limits, but all of that is private. So, yeah, you're basically constructing a share and an internal nullifier that correspond to the same, it's essentially the same thing, except you just have this message ID that is between 0 and the message limit. And that's essentially how we can have an arbitrary number of messages per an epoch. So this is kind of like a high-level overview of how our circuits work. So you have a secret and the message. So the message is in the center here. I don't know if you can see this.
Yeah, we can see it.
Okay, cool. Yeah, the secret and the secret trapdoor nullifier is what makes up your like secret identity, right? And so that goes into the circuit. The external nullifier, which is essentially your RLN app identifier and the epoch hashed together, which was shown in a previous slide. Then the message, your message ID, and then the message limit. And then what comes out is this internal nullifier, your Shamir secret sharing share, and the Merkle root. So with this Merkle root, you can prove that you're a member of a Merkle tree without revealing who you are. The share and this share is useless on its own, but if more than one message pops up with an internal nullifier that matches during an epoch, then you can take those shares and combine them to recover the secret. So the message limits are...
Tyler, just to clarify to fellows, so when you are saying you produce a share, you prove that you know a share and you're releasing it, that's someone who wants to send a message, and then people verifying that that's the whole network as overall. And the whole network is when it receives multiple shares from the same user is able to reconstruct the entire secret. So by you here, it means a user in the network, in the P2P network.
Yes.
Okay.
All right. So, all right. So I think Russell is going to go over the message limits a little bit more. So I'll leave that to him. All right. So how this is practically used is a user can register on some smart contract, for example, and they can stake some amount of money, and then they can send messages throughout the network. And as long as they don't break the rate limit that they're committed to when they register, then everything is fine. They can message anonymously and they won't ever get found out. If they message too often, then someone else can recover their secret, prove we have a Circom file that you can prove that you know the secret of someone else to be able to withdraw their stake. So essentially that someone else can remove their stake, so there's some financial incentive to try to check other people's work, and they will get kicked out of the system. So they can re-register theoretically, but that depends on like how you want to gatekeep the registration to begin with. So there's the financial stake, but you could also require that they own some NFT or that they, have some amount of ERC20 or something. So there's other barriers to entry besides just the stake. All right, so the building blocks of this, we have a library that we're working on called RLN.js, and I'll cover this quickly because this isn't really dealing with the circuits, but we essentially have a JavaScript library that handles the registration, the slashing. It can generate the proofs for the messages. It does the secret recovery for you. It caches all the messages that are coming in, so it will automatically match internal nullifiers and recover secrets for you. And then we have, I think the contracts are pretty much done, but we have contracts to be able to do ERC20 staking, be able to slash users, be able to withdraw, and yeah, I'm not going to do a demo now. Our demo's changed and is broken. I can get into some of our challenges. So we've solved a lot of these, I think, but front running is definitely still kind of a challenge for us. If someone else can withdraw their stake or something like that, then they, a front runner could be able to try to use the same message to be able to withdraw that stake. That's one of the reasons why we're using ZK proofs, because we can, for the withdraw, because we can use the EOA that is calling the contract to withdraw as an input to the proof, so no other EOA can try to withdraw that.
Tyler, could we take a question from Pratyush, who raised his hand?
Yeah.
Hey Tyler, how's it going?
Good. How are you?
Good. My question is basically about the nullifier tree that you have. How many levels do you have in that? And have you guys explored like the newer solutions that give you a linked list of the leaves, and one like leaf points to the next larger one? And I know it gives you like some improvements when adding new members to the nullifier, especially in huge trees. So I was just curious if you guys have explored that yet.
So our circuits are using incremental Merkle trees, and I think our default tree depth now is 20, but that is configurable. You can change that. Yeah. So we're planning on doing trusted setup soon, and we'll do multiple versions. So probably a tree depth of like 16, and then of 20, and then maybe even greater.
Yeah,
there are.
I guess like at this tree depth, it doesn't really cause issues, right?
Sorry, can you say that again?
I was saying that the depth isn't like high enough for this to hit like any huge performance bottlenecks. This would probably become an issue when you go beyond like depth, like 100 or something like that.
Yeah. There's some other mechanisms that we're researching right now to be able to prove that you're a member in some set that does not use Merkle trees. There's
like
Hawk, there's Hawk Plus. Yeah, exactly. Yeah, Russell can answer a lot more of that. He understands a lot more of the lookup stuff than I do.
So Tyler, registry and cache here, we're talking about smart contracts, right? They get deployed after the instance has been initialized above?
Yes. Yeah. So these registries are every client that's trying to check other people's messages, they keep a local version just so they can quickly check, but that's essentially a mirror of what is on a chain in a smart contract. Yeah, we can actually just go into questions now. All the challenges, like money laundering and stuff like that, this is kind of outside of the scope of learning ZK.
I think we can actually say, do you have like, I don't know, any slides on front running problem maybe, or yeah, front running, you have front running, because we have withdraw circuit and that like actually prevents front running. So we can talk about this.
Yeah,
or
you want
I
to talk about
that? I can talk, and maybe I can already go through the code and like explain it.
Yeah,
like,
that sounds good.
I don't know.
I think, guys, it would be helpful actually to take just a use case and go through the steps from registration, from generating the instance, and what the challenge would mean in that context, for example. So if you have just like a quick example of an application, an RLN instance, basically.
Yeah. Let me find that slide.
And while Tyler is doing that,
Um,
Rasul, let me ask you a question.
Sure.
So the P2P network is incentivized to look at incoming messages and seeing if they have received enough share to reconstruct the secret. And with that, they can prove on chain that someone has exceeded the limit, and they slash them and get rewarded. So I guess this is a basic question, but if someone sends floods the network with the same message, for example, or they try to do something malicious, so just like in general in P2P network, the peers will basically just drop and not forward the message, basically, right?
Yes, yes, yes. So it's like message repeating problem, and any like this kind of stuff is solved by like networking layer. So it's like not the not solved by ZK stuff. ZK stuff is only like for different messages, and if the different messages is like coming from the same user and they exceeds the limit, so they will be slashed, something like that.
Yeah, perfect. So just to clarify to fellows, the network, whatever happens at the network level in terms of DDoS resistance is not part of what we are covering here. This is something, it's an old problem, and you deal with it by actually choosing to not receive messages from that user, or obviously not forwarding their message. So it's outside of the scope, basically, that networking layer components.
Yeah.
Okay, so this is kind of an overview of the circuits in like a more organized way, so you can see how they all connect, how the pieces connect. But yeah, so essentially a user would take a secret. So in this scenario, it is we're using two random values, one a trapdoor and one is called a nullifier. And those are hashed together to create some secret. And that is the value that is used to commit your identity to the Merkle tree. So you would hash that, and that would be one of the leaves of the Merkle tree. So that would be your registration process. Like you would put some stake with some identity commitment and message limit, and you would commit to those values on the contract with 10 USDC or something, and that would be the registration. And then for someone to be able to slash you, they would have to be able to recover your secret. So Russell, do you want to kind of take over and go over the circuits, and if anyone has any questions about the smart contracts, we can go into that also.
Sure, sure. So I can share my screen. Can I do that? I think I can. I think that would be good. Do you see my screen?
Yes.
Yep. Yeah, I wanted to start from so current RLN version, and like the version that you're going to audit is kind of like a new version, newer version, and has some like new features. I think it will be like more simple to explain first, like old version first, because it's like simpler. Yeah, so here we have like three like circom files. One of them is just a template file for Merkle tree. Do you see my screen? Everything's fine?
Yeah, everything's fine.
Yeah, I think I won't go through the like deeper level of explanation. It's just basically like Merkle tree, like the same like Merkle tree that is used like in semaphore protocol, in Tornado. So yeah, Merkle tree is Poseidon hash function. Yeah, and here we have also two circuits, like two main component circuits. I will go with RLN circuit first. So yeah, here we have three private signals. It is identity secret. It is like the value that Tyler was talking about, like when he said about secret and trapdoor. This is like the secret that is generated by user. These inputs are for Merkle tree, is like sibling nodes and the hashing road. Public signals are X value. X is just the hash of the message that user sends. And external nullifier, it's like basically hash of epoch and RLN identifier. I think Tyler actually also mentioned that before. And like what is like outputted by the circuit is like Y share of the polynomial root of Merkle tree and internal nullifier. Here it's just called like nullifier. So we have basically three constraints. We can even say probably two constraints. First, it is like membership proof, and second is like we proving that we calculated the share correctly. So here we're doing like basically Merkle proof. We're calculating the identity commitment, calculating root of Merkle tree, and then we calculating Y share. So Y share is calculated as polynomial identity, like identity secret is like is our secret, and as you can see, it's like is the polynomial of first degree. So any two shares can be used to recover the identity secret. Yeah. What can I say? What else?
So in this case, Rasul, in this case, the user can send at most one message.
Yeah.
Without being slashed.
Yeah. The user like during like for a unique epoch, user only can send only one message, and that's actually why we implemented like newer version, and newer version allows us to send more messages, to set higher limits. I will go through that also. Like, and here we're calculating internal nullifier, and basically, if, for example, user will send two different messages during one epoch, nullifier is calculated as Poisson hash of A1 value, A1 coefficient, and A1 coefficient is just identity secret and external nullifier. So during one epoch, the nullifier will be the same for the same user. So any like P2P nodes can like check if the like nullifier internal nullifiers are repeated somewhere, then like some user are like spamming and they can be slashed. So any questions on that, like for now?
So with two messages, you have 2 points, 2 Ys, and with 2 points, you can reconstruct a line basically, and that's how you know the secret. And then
2 X's and 2 Ys. 2 X's and 2 Ys. Like share is the like tuple of like pair of X and Y, X and Y. Yeah. So yeah, with any two points during one epoch, you can, from the same polynomial, you can like recover the polynomial and like recover the secret value. Yeah. So for that, it's just that's it. And we also have actually front running problem. So I don't know if I should go through this problem right now.
So Rasul, just to describe what we're seeing here, so we can think of the first circuit, incremental Merkle tree, as initialization of a DApp. RLN is ongoing execution, and the last one, withdraw, is termination, when the user wants to terminate and just exit the application. Like
Yeah,
one,
we can
if
say
we
it
can
like
think
that.
of it as an app basically, and as an app execution overall.
For registration, you don't need to make like any ZK proofs. For registration, you just send your identity commitment. You just hash your secret by Poseidon hash function. You just hash your secret value and send this commitment to the like smart contract. And every client will add your identity commitments as a leaf to the Merkle tree that used in the app. So we can say that this Merkle tree circuit, this Merkle tree template gadget, or however, is used for interaction, basically, not like finishing the the like application process, but for the interactions, like to send the messages to prove that you are a member of the like some set. Is it okay?
Yeah, that makes sense. Thanks.
Okay. So we also have front running problem. I don't even have to explain that. So imagine a situation when like you slash someone, and you want to now claim a stake, spammer's stake, and it is like it can be claimed from a smart contract, from registry smart contract. And how you can do that? You can do it that, for example, by sending like directly without any obfuscation, just identity secret, right? And it will be hashed on chain and checked if there is identity commitment that is like hash of this secret. And if it is, you can withdraw the money. So that's good, but that's basically allows everyone, like miners or everyone, to repeat your transaction and to receive the reward. So the thing that we need to have is we are slashing by making ZK proof that we know some identity commitment from the like registry. And that's just a super simple circuit. As a private input, we have identity secret, and as a public input, we have like address, hash of address, or just address. I don't know if like you checked Tornado Cache code, Tornado Cache implementation. They also have like recipient in their circuit. That's that value is used like to prevent like I don't know, like validators or anyone to change this value in the circuit and to claim the stake. I don't know if I like am explaining good. Any question, guys? Because it's a bit tricky to explain.
Yeah, if you don't mind explaining that part, what did you mean by trying a different address and exploiting that?
Imagine you don't have this in the circuit, this public input, and you made a ZK proof and you want to send it to smart contract to receive identity commitment. Anyone, for example, a relayer, can just send it themselves, send your ZK proof and claim a reward themselves. So they will receive the reward and not you. And you want to prevent this kind of attack. So you like kind of making your address, Ethereum address, where you want to receive the money, where you want to receive the stake, you're making it public input. So if anyone change it, the proof will be incorrect. So no one can change it. And if you made the proof with your address, with the Ethereum address that you picked, only you will be able to receive the stake reward, like that.
And so if a user is withdrawing, a user who did not spam and they just want to withdraw their stake, if they simply send an Ethereum transaction with the proof that they know the identity secret, someone,
Yeah.
an MEV searcher, for example, take that transaction, remove the recipient address and put their own address, right? And so you are restricting the address to which the withdrawal goes to as part of the circuit itself.
Yeah, exactly. It is like the same problem as in Tornado Cash. So they use relayers, right?
Yeah.
Like the thing to not pay for transactions, basically, and
Yeah.
they can just basically repeat your transactions and claim and withdraw like your money that you staked there. So it's just prevent this type of attack.
Yeah, that makes sense. Thank you.
Maybe anyone has any questions on that, or everything's just fine and I can go further.
Yeah, Vincent's asking the withdrawal circuit. Why are we only hashing the identity secret and just putting out the output? So
and what else should we need to do? Because like it is enough. It is enough. We have like registry on the when we slash or withdraw, which is basically interacting with the smart contract, and we don't have like any Merkle trees on chain, so we don't need Merkle proofs for that. We just basically can output identity commitment from our ZK proof and send this proof to like smart contract, and smart contract just can check like as identity commitment is like public. You can say output is the same thing as public input. So as identity commitment is like public value, it can be checked if this identity commitment is in the membership set, in the mapping basically, and if so, the proof is like correct. Yeah, does it make sense? Or someone asked, oh, everything's fine.
Yeah, so I guess the withdraw circuit, Rasul, we can also call it withdraw or slash, because it's the same circuit that appear in the network with execute in order to slash someone. It's also called a withdraw as well.
Yeah. Basically, slashing is like also like the thing when you are withdrawing the money, withdrawing the stake. That's why we call it withdraw. But yeah, slashing is more situation when a user like exceeds the limit and someone recovered their secret and then withdraw. And like just simple withdraw is just when user is not like a spammer and they just withdraw simply their stake when they don't want to use RLN app anymore. Yeah, like that.
And of course, when there is a slashable case, the peers in the network will try to produce this proof as fast as possible and get it to L1 first,
because
basically.
like L1 or L2, like wherever you use wherever you deployed the registry.
Could you also give an intuition, just a quick intuition as to how on L1 does the contract check that this user has already been slashed? So there is a second slashing proposal to the L1, but it has already been slashed. Is it simply that the fact that the stake is
we
gone?
don't check. We don't check that it was already slashed. We just remove the identity commitment from the membership set and emit an event. So like every like other nodes can remove it from their Merkle tree also. And that's just basically it. Like if someone is slashed, it like won't have like opportunity to send any more messages because ZK proofs won't be correct.
So the like L1 contract, in addition to checking the proof, it checks that the membership.
We can go through the
ongoing.
Contract if you want. Also, we can go through the contract if you want. Also, 1 second. Should I or?
Yeah, I think so.
1 second, okay. I don't know what's the problem. 1 second, okay.
Yeah, while you're on that, Rasul, my question was a bit like kind of general, the proof is correct, but the contract also validates that the membership is ongoing, or is it just that simply the stake is already gone, so the second slashing transaction does not result in it, just wastes gas basically. You can speak to that, Tyler, while Rasul is getting ready.
Sorry, I was typing out the answer. So X and Y will be, oh, Zoom loves to go full screen. Okay, so X and Y will be posted on chain in events. No, so I'm assuming by X and Y you mean the share from the user. So all of that stuff, like all the messaging, and it's like, you know, let's say if I'm part of an anonymous network and I want to message, I will send my message along with my proof and the internal nullifier and the share. And that will go on some other communication protocol. So that could be like a chat program or something, or like, you know, over libp2p, or yeah, some other networking mechanism. And so the only stuff that needs to happen on chain is the registration and the slashing and the withdrawals. Like the actual messaging and everything can happen totally somewhere else.
Yeah. I also can add here that we need we only need RLN probably in I mean I think 99% of time we need RLN in no consensus like layers of network. If we don't need like messaging and use, we don't need to use like RLN exactly on chain. I mean directly on chain for messaging, because on chain we have like other methods to constrain user. For example, we can just basically use semaphore and have a limit for the same nullifier, something like that, to prevent exceeding some limits. And in no consensus layers, so like in non-consensus systems environments, we actually need RLN. And smart contracts is only used for like registry, and that's it. Like to register and to withdraw and or slash someone. Does it make any sense?
Yeah, that makes sense generally. Guys, if you have two slashing transactions, they're both valid and they are towards the same user, it's the same slashing event, and they are executed in the same block, L1 block, one after the other. What is the, just generally, you don't have to dig into the code, but generally, what happens to the second execution, the second slashing? Does it revert?
It won't be correct. Yeah, it will be reverted because first transaction already like removed the identity commitment from the membership set, and when second transactions like will happens like ZK proof won't be validated, won't be verified as a correct proof because there is no identity commitment in the membership set.
Yeah, perfect. Thank you.
I can go through the contracts fast also. I mean, not just super deeply, but we have like here constructor, we have like ERC20 token for staking, we have here verifier contract, like other parameters like depth of Merkle tree, set size, deposit for the message. Yeah, I won't go through this thing because like it is not in the scope of the audit. So we have like register function, withdraw function, and slash function basically. So the difference between withdraw and slash. So withdraw is when the receiver address, address that will account that will receive the stake is the same account that was used to register the identity commitment. We called it withdraw, and slash is like when someone else is doing that, like removing member from membership set. Yeah, no, like that basically. Nothing special on the contract side. Any questions on this?
And the call data is basically the same in both slash and withdraw. It's a proof.
Yeah. And it just checks whether like receiver is like the same. You can go basically yourself through the contract, and also, of course, you can like ask any questions in the chat later. Like RLN contracts is also in the same organization that where we have like circuits, so you can go quickly.
Could you go to the
RLN.
withdraw function, Rasul? Could you go to the withdraw function?
Yeah, we can go through the withdraw function. It basically
no, just a quick question. Just a quick
okay.
question about withdraw. I don't see message.sender anywhere in it, so I'm just
we
wondering.
don't check message.sender. We have a receiver here, so we actually use a receiver address here.
Oh, makes sense. Okay.
Here or like here also. Yeah, and for slashing, I think we have this thing, receiver. Yeah, we just like pass it to the call data as a call data, not use message sender, because for example, if we use relayers also, it will be like useful. That's why we don't use message senders. Fine. Should I go
that's much
further?
No, that's it's very clear, and it's much cleaner way of doing it. You are correct. So that, you know, it doesn't have to be hard-coded message to sender, hard-coded into it. So yeah, makes sense.
Yeah,
thank you.
yeah. Okay, like should I go like to the like current circuits that you guys will audit, or you have any questions on the like contract also?
There is a general question from Igor about the incentive of a peer on the peer-to-peer network to actually forward messages as opposed to just silently receiving messages. And this is, I guess, on the network level. You can answer it, Rasul, you know better, of course, but probably if you are not participating as a peer, the network as a whole do not know about you. So you will, over time, the network will start dropping you, I guess.
I mean, it depends on application. It depends on application, because like there are a bunch of like applications that can use RLN. For example, RLN can be used in like for validator validator privacy, and like not exactly for privacy, but for spam prevention on validator level. It can be used in like in then like any P2P network, like in BitTorrent and like I don't know, Onion protocol, Tor protocol. So it's kind of the question more not why should I be a node in the for the RLN protocol, but why should I be in a node for some high level like P2P protocol? It's like I think more like that.
Yeah, it's a question between active and passive node on the network. So we take an Ethereum node, for example, if it modifies the code base such that it doesn't forward messages, just silently listening to save bandwidth, for example. And my guess is that at the P2P library level, at the node level, there will be a logic that says, you know, I haven't seen this peer in a long time, so I'm going to stop forwarding. I'm assuming that they are offline because I have not received them. So inactivity will probably make you go offline, basically, effectively. This is just a general question. Obviously, it's outside the scope of RLN.
Yeah,
I think.
Yeah, it's just outside of the scope. I think. I mean, we can talk on this also, but it's like it's not related directly to RLN. So RLN is just the tool that helps for any like P2P protocols.
Yeah. Protocols like libp2p, they have peer scoring mechanisms built into it, depending on like what messaging protocol you're using within it, like gossip sub or flood sub or pub sub or anything like that. There's peer scoring mechanisms that like you can just listen and pass messages along and not actually be a user or be registered, and you can still slash. So that's an incentive actually to have more clients monitoring for malicious activity. But if they don't pass messages, if they just receive messages and they never pass them, then their peer score will go down and people will disconnect.
Yeah, that's great color. Thanks, Tyler.
Okay.
Rasul, is there something specific next you want to go to? Or maybe if I make a suggestion, we went over the simple initial version that you guys implemented. So could you go over one example of something that changed and is now present in the latest commit, something that you guys added?
What do you mean like it's not present in latest commit?
What is a major feature that you guys added that exists now in the latest commit we're looking over and did not exist in that initial simple version that we were looking over, those 3 circuits?
No. You will be looking into new like the latest version, not the version I showed you before, because
yes,
like
but what is
version is just
an example of something implemented now in the latest feature we're looking at, but was not present in the original one?
Basically, what is like the main thing we wanted? Even you asked before. So in like those circuits in like alt RLN, we can call it alt. We have like first degree polynomial, right? And we have like a limit of one message per epoch. So actually, maybe there are some cases where we want to set like higher message limits, right? It will be good. And actually, other thing we might want to have, we may want to have, is just to set different rate limits for different nodes, different users, right? That would be like, for example, based on their stake or based on their reputation. So that's the thing we want to have. So actually, that's the thing we added to the new circuits. And how we did that. For the withdraw is basically the same thing. I won't go through it. And here we also added two additional inputs, private inputs. It is like user message limit and 1 second, I will. User message limit and message ID. So what is going on with user message limit and message ID? Basically, when you are now registered to a system, to an RLN app, you, for example, you send a stake, right? You send some amount of stake, and based on the stake you attached, your message limit, your rate limit will be calculated. So for example, the cost of one message, price of one message is for example $1, and you attach $10, 10 USDC, for example. So your message limit will be 10. And now it is like not the identity commitments that are stored in the Merkle tree, but rate commitments. And rate commitments are calculated as Poseidon hash function of identity secret and user message limit. Is it clear for now?
Yeah, I think linking the message limit to the amount of stake is a really cool idea.
Yeah, I mean, like, everything's clear. Should I like any questions like for now, or should I continue?
You can continue. I don't see any hands being raised, so
Yeah.
you can go ahead.
And what we are doing now, for every message, we also have like this input, private input also, message ID. It is like used as just a counter, just temporary variable, and we check that this message ID is in range from 0 inclusively to value user message limit exclusively. So it's just basically you have user message limit limit of messages is set to your user message limit. So as Tyler said before, when we like wanted to have like to set higher rate limits for everyone, we decided to go with like higher degree polynomial to have like more shares to recover the secret. But it is like not very good because there will be more hashings in circuits. The circuits like is getting more complicated with that, and with just additional private input, it's just nothing special. We just check that first we calculate rate commitment here, then we still like check membership. We calculating the root, and the next thing we check actually is that the message ID is less than user message limit, is in range from like is an interval from 0 to like user message limit. And you can understand that now we can have like higher message limits, higher like rate limits, but the degree of polynomial is still first. So it's just as simple as it was before. And the only thing that like other thing that was changed is that we calculating A1 coefficient as the hash of identity secret, external nullifier, and message ID also. And if you will use the same message ID, the same like credential, the same message ID twice during the in epoch, nullifier will be the same, and you can be slashed basically. And for example, if message ID will be not in the like interval from 0 to user message limit, Zk proof won't be verified. It won't be like correct. So basically like that. Yeah, I think that's it. Now you can ask questions.
So in this case, with this new trick, Rasul, how can the peers reconstruct? Can you explain the part where the second point that allows us to reconstruct a Y happens in this case, if someone exceeds their limit, because they are
So,
not. I don't see.
Let's imagine situation. Okay. For example, you have user message limit equals like to 10. For example, you have 10 messages limit, 10 like yeah. And now you have I will go through like the case when it is like the same external nullifier. Okay, so it's like the same epoch, because we are going to talk about like how we can slash. So we have one polynomial. When we want to send a message, we like inputting these private parameters, calculating rate commitments, like proving membership. This is fine, okay. And now we are, for example, we are using message ID equals to 0. It is our first message, for example. So we will have for this message ID, we will have polynomial identity secret plus A1 multiplied by X, and A1 here is Poseidon of identity secret, external nullifier and message ID. So we now have like unique A1 coefficient for 0 message ID, right? Is it clear?
Yes. And then
yeah. And then we like outputting, like everything's fine. We send our message. Now let's imagine we are sending it again. We now should use message ID equals to 1, right? Because for example, we now use message ID equals to 1. Now it will be like again different polynomial because A1 will be different, right? Message ID is not like 0 anymore, it's like 1. And imagine you are doing this 10 times. You send your 10 messages. Now you like, it is like the limit for you. If you send one more message, you either get slashed or the ZK proof will be incorrect. For example, you used all your message IDs, right? From 0 to 9 exclusively, inclusively, right? Now, for example, imagine situation when you use message ID equals to, for example, 15. And this will like rank check will be like failed because 15 is bigger than your user message limit. And actually what prevents you to input other user message limit is that you committed to the value in the registration phase. So the case
why is the range check not enough now? Why do we still need to constrain Y?
No, because we just simply need to calculate the share. We need to calculate the share, right? To be able to recover the key, to be able to recover the secret key. And now imagine the situation when we use, for example, value we used before, for example, 8, let's say, and we use 8 before. So A1 value will be the same, and the polynomial will be the same. And if you send some other message, like every node will receive 2 different shares from the same polynomial and with the same actually nullifier, and they can easily reconstruct your polynomial having like 2 shares and like slash you, so basically like that.
One thing I don't see, I don't know about everyone, but one thing I don't see is how the Y is different in two messages that use the same ID. So A1 would be different in both of them. That would be 2 points, but I see them as the same point because identity secret, external nullifier, and message ID are all the same in both cases, right?
If we use the same message ID twice, you mean? Yeah, it will be the same. That's actually what helps us to prevent spamming, because if we use the same message ID, the same A1 will be calculated. And if you do this twice, you will output 2 shares from the same polynomial, right? And that will help, that allows to slash you, to recover your key, to recover the identity.
So the Y share will change because of the actual message, like the X will change, and but the nullifier will be the same, which is what you want.
Yeah, if we use the same X value is just the message value. We can just prevent this on network layer because the message is the same. we can just like deny this
Oh,
message.
nice. Yeah, perfect. Yeah.
Yeah,
So
and
it's-
if we use like two different messages, y y value will be different.
Yeah, so it's the x that forces the reveal of an extra point on the same polynomial.
Yeah.
Thank you, guys. Perfect.
Yeah, basically like that, I think. And for the contract, we actually also here that I like didn't show you before. We have here like minimal deposit value. It's just the cost of one message. And when we are like making registration, we are attaching the amount of tokens we want to, and we are basically calculating the message limit. And then when member is like registered, we emitting the event and emitting like identity commitment and message limit. And every client will like to do Poseidon hash on chain, because like it is expensive. We are outsourcing this to like to clients to do it themselves. Yeah, basically like that.
Yeah, Poseidon itself is constrained, so it's done off chain.
Yeah.
Yeah, it's great that you went over the contracts, because I know some of the resident auditors at Y Academy are kind of shadow following this ZK fellowship. So, and this is their domain. So they will be, I think it will be good to have their eyes on these contracts as well.
Yeah, that would be really cool.
Yeah, all ZK things aside, I think we will benefit from them lurking and poking at these contracts for sure.
Yeah, and also if you have like any question, because there is some logic I didn't go through right now, because I think it's not in the scope of audit. But if you like read the contract, go through the contract, and you will have some questions, you can ask us.
Yeah, there is a question from Emmanuel about the prover time. Or the prover performance generally.
Prover time actually is like there is not big amount, like not many constraints. It's just, I think for Merkle tree of depth 20 is just 5,800, I think. So it's like not too much, because we use only snark friendly primitives. I think it's like nearly 1 second for Snark.js, and for other provers, I don't even know. I think it should be faster with Rapid Snark and other stuff. Yeah.
So in general, with R1CS,
what we
sorry, Rasul. So in general, we would worry when the number of constraints of R1CS is in the millions, for example, right? That's when things get really expensive.
Yeah. No, not
so
even
5,000 is really low.
Yeah, 5,000 is really low. Yeah, and with draw circuit, I don't remember, it just have 300 constraints or something like that. Super basic.
Wow.
Something like that. Yeah,
that's really small. Yeah, that's amazing. Okay.
Yeah, but yeah, it's a good question, because for example, for some low level stuff, as for validators, or for like in Tor network, like in ONM protocol, it is good to have like fast proving time, right? Because even 1 second can be slow. We working also on other things, like RLN, basically just on KZG commitments. But I think I don't think that's in the scope of the audit.
Perfect. Any more question, guys, before we wrap up? We could take a few more questions. while everyone thinks of a question maybe and type it in the chat, I'll ask you, Rasul, have you guys manually tinkered with the resulting R1CS constraints? Did you do any manual optimization at that level, or did you just take whatever came out of the circumcompiler?
We didn't do actually optimizations. I know that there probably should be some optimizations, but I won't tell about this. I won't tell about this. Let it be a challenge for fellows.
Okay, excellent.
Yeah, no, it's not a super big optimization, but I'm not even sure that if you guys find this, we probably will change it. If not, we will probably don't even change it. So it's like
okay, so it's a hidden treasure for to see if someone can find that.
No, it wasn't intentional actually. It's just like, I don't know, even we would optimize like constraints. Really, I'm not sure. I think it should, but so
okay.
it's not that like important actually. But yeah, we can see.
We can see, yeah. I think, fellas, there is a straightforward way for you to get a hint of what that is, but I also will not give that hint, and I'm also not sure if it's correct or not, so I'll just keep it to myself for now. Antonio, yeah, about looking at the starting the audit and sharing the issues, yeah, you can do GitHub issues, or as we said, guys, during orientation, you're encouraged to work in groups if you want to. So we leave that up to you to self-organize into groups. You can even have your own calls. You can tell us on Discord that you're having a call, and some people would hop onto it if you want to have a live session and chit chat about the audit. But we will see if we can have an office hour maybe one time if Rasul and Tyler have time. But if not, they will be present in Discord to answer any questions. I should also mention that we may next week have one or two speakers that come and speak about some lower level part of the Circum pipeline that happen under the hood, like the trusted setup or the pairing and things like that. But you don't need to, for the sake of this audit, you don't need to know those. We're trying to go step by step and not overwhelm you with everything, basically. So yeah, keep the discussions going, ask questions, self-organize into groups if you want, hop on calls if you want, publish them for anyone to join if they also want. And yeah, I don't see any further questions. So Rasul, Tyler,
I also wanted to say, like, if you have the questions, please tag me or Tyler, okay? Because
yes,
notifications like not always are coming.
Yeah,
so
yeah. I will edit the announcement to include your handle and Tyler's handle so that everyone knows you guys on Discord. We appreciate you coming in. This is an amazing starting code base. It's a nifty thing, and it's it has many amazing applications, obviously. So excited to be looking at it and excited to see it adopted by other apps. Basically, I describe it as a ZK dApp, but maybe the more accurate thing is it's a library that can be plugged into any P2P applications. So
library protocol.
Yeah, exactly. Yeah. So this has been amazing. Thank you so much, Rasul and Tyler. Thanks to the fellow, and we will see you guys on Discord.